The last topic in our gas chapter deals with mixtures of gases, right? And the nice thing about this is we're dealing with ideal gases. So we remember some of the assumptions of ideal gases, and that actually leads to a pretty simple and straightforward way of dealing with mixtures of gases, okay? So what happens when I have a container that doesn't just contain one gas, it contains multiple types of gas as well. If those gases are ideal, then what we assume is that there are no interactions. They never bump into each other. They do not see each other. So it's almost like to this blue gas here, there are no red or purple gas particles. So it has its own individual pressure. It exists in this space. And if we assume, if we make this approximation that it doesn't feel a red or a purple and it never bumps into a red or a purple, then it exists by itself independently. You can make the same arguments for the red gas and the purple gas. They're in there, they don't see each other, they each are their own individual ideal gas with their own individual ideal gas equation. Well, with that idea, this guy named Dalton came up with Dalton's law of partial pressures. Now, whenever you see this word partial pressure, think about it as an individual pressure. So red would have a certain pressure inside here. We call that the partial pressure of red because it's part of a mixture. It has its own partial pressure. Well, what Dalton's law of partial pressure says, it's a real simple, sort of straightforward formula. The total pressure inside here is simply a sum of all of the partial pressures. So if I know the pressure of red, and I know the pressure of blue, and I know the pressure of purple, all I would do, right, we'll remember what summation notation means, all I would do is take all of those individual pressures and add them together to get a total pressure, okay? Now, one of the consequences of this formula, and that's it, that's how we deal with mixtures of gases. Whenever you think you have a mixture of gases, you write down Dalton's law of partial pressures, okay? So one of the consequences of this formula is we can start to calculate what are known as mole fractions. Now, mole fraction is actually a concentration, okay? Now, it's not a molarity, it has different units, and we deal with mole fraction a lot more next semester, but we do need to know about it this semester. Mole fraction is given the Greek symbol chi. Every particle in a mixture has its own mole fraction. So we kind of label these chi sub I, where the I would stand for red or blue or purple in the context of this example here. Okay? Chi sub I is the number of moles of that one species divided by the total moles of all gases all added together inside a sample. Okay? So if I know the moles of red, and I divide that by the moles of red, blue, and purple, that is defined as mole fraction. Well, it turns out you could also calculate that same value if you took the partial pressure and divided it by the total pressure. So there are two different ways to calculate mole fraction for a mixture of gases, and you need to know both, okay? So just as a review, because whenever you see this keyword mixture, or whenever you notice that a problem is telling you there's more than one gas in a sample, right? Then you have these three tools to work with. The total pressure is the sum of the partial pressures. If it asks about mole fraction and it gives me mole information, mole of the part divided by total moles is mole fraction. If it asks for mole fraction and you only see pressure information, then you take the partial pressure divided by the total pressure, and that will give you the exact same mole fraction that you would get if you knew the moles and the total moles. Okay. So we're going to do an example. We're actually going to do this example two different ways just to explore the different ways we can calculate mole fraction. Just to introduce you to using all of those equations, right, in one nice little tidy setting, okay? So for this example, we have a mixture, and in that mixture we have oxygen and neon. All right, and they're both gases, and they're in a mixture. Now, I'm going to give you some properties of that mixture. And like I said, we're kind of going to do this problem in two different ways. So in that mixture, we have 0.10 moles of oxygen gas. And in that mixture, we have 0.050 moles of neon. That mixture is encapsulated in a container. And the container is 1.0 liters in volume. So this, because both these gases occupy that container, this is the volume of oxygen and the volume of neon. Okay, so this belongs to them both. Okay, the temperature, all right, is 25 degrees Celsius. If that's the temperature of the container, well, what's inside the container? Oxygen and neon. So this temperature belongs to both those species. And so what we're going to do is we're going to calculate a total pressure. And then we're going to do this in two different ways. We're going to calculate chi oxygen and chi neon. Okay? And we're going to do this using moles and then also using partial pressures. Okay? So just to make sure you kind of get it, let's draw a little picture. Let's say that my purple is my oxygen. Right? It's inside a container. This container has a 1 liter volume, 1.0 liters, but you get it, right? And everything inside that container has a temperature of 25 degrees Celsius, right? Now let's say we have pink particles representing the neon, right? Well, what's the volume of this neon gas? It's that same volume, 1 liter, okay? And the temperature is going to be the same because it's in that same container. Now we see we have a mixture of gases. So how are we going to be able to calculate the total pressure? Well, the total pressure is going to be a sum of the partial pressures. So what I have to do is I have to use the information provided and calculate the pressure of O2. And then I have to use the information provided and calculate the pressure of neon. Once I have those two values, I can take them and I can add them together. And when I add them together, I will get the total pressure inside this container. Right? So hopefully that makes sense. Well, if you look at this, right, how am I going to calculate the pressure of O2? Well, what I need is the number of moles of O2, or the temperature of O2 divided by the volume of O2. Right? What about the pressure of neon? I need the number of moles of neon, or the temperature of neon, and the volume of neon. Now, both these guys are in the same container. So remember, T of oxygen is the same as T of neon, and we really can just call it T. And V of oxygen is really just V of neon, and we really could just call it V. All right? So another way of writing this would be the number of moles of oxygen plus the number of moles of neon times RT over V. Okay? Remember, if I have a common factor, if this T is the same as this T, and this V is the same as this V, I can factor out the common factor RT over V from this sum. And so this is what I get. So think about everything that we have now, right? Do we have a number of moles of oxygen given? Sure. Do we have the number of moles of neon? Absolutely. Do we know R? Yes. What am I going to do to this temperature to make sure I get the correct answer? I'm going to convert it to Kelvin. And do I know what the volume is? And we're going to use the correct measurement for this volume. And the answer is yes. So we have this set up now, and you guys are getting good at using the ideal gas law. And what you should be able to show is that when you do this math, you get a total pressure of 3.6699 atmospheres. There would be two significant figures there, right? We're limited to significant figures here. And also when you do this addition of moles, you end up with two significant digits. Okay? So that is the total pressure. That was the first thing we were told to calculate. That's great. So now, in two different ways, let's go ahead and let's calculate, all right, the chi for O2 and the chi for Ne, right? The chi for O2 and the chi for Ne. So please, I'm going to erase this, but please kind of keep in mind that you have the values to continue this example. So the easiest way to calculate chi of O2 is to find the moles of O2 and divide by the total moles, right? Well, I have all that information like readily at hand. I know I had 0.10 moles of O2. Inside that container, there were 0.10 moles of O2 and 0.050 moles of Ne. So my total moles is found by adding those two together. Now we remember our rule for adding things, okay? This is good to the second decimal place, so when I add 0.05 to it, it's really 0.050, but I would be stuck to that second decimal place in terms of, all right, limiting my knowledge of that addition, okay? So when I do this and I put in my calculator, I get 0.6 repeating. And to two significant figures, the mole fraction would be 0.66. Mole fraction is reported as a unitless quantity, and we just realized that if we're talking about chi of O2, there are 0.66 moles of O2 for every sort of total mole inside there. It's like 66% oxygen is another way of looking at it in terms of moles. What about chi for Ne? Well, I need the number of moles of Ne, and I need to divide by the total moles. Well, the moles of Ne were 0.050 moles. It exists in the same total moles inside that container, inside that drawing with the dots that we had before. If I do this division, I get 0.3 repeating, right? I can show you the other non-significant digits. So in terms of like percent moles, it's like 33%, but we would report it as a mole fraction. The mole fraction of Ne in that sample is 0.33. An interesting property of mole fraction, right? I have two species. What happens when I add those mole fractions together? I should get 1. And when you do problems, that's a nice little check. Does this work out? If I take a fraction and it accounts for everything inside a total, the fractions add to give you the whole, right? So 0.6 repeating plus 0.3 repeating definitely gives me 1. So this gives me confidence that these numbers are correct. Okay. Now let's calculate the mole fraction in a different way. Right. We should get the exact same number. Chi of O2 would be equal to the partial pressure of O2 divided by the total pressure. Now from our previous work in this example, we know what the total pressure is. So can we calculate the pressure of O2? Well, sure, I can calculate the partial pressure of O2. The pressure of that part of the mixture that is just O2. And what I need is the number of moles of O2, RT over V. And what you should be able to show is that you get 2.4466 atmospheres of O2. So I can come up here, and what I can do is take my 2.4466 atmospheres of O2, and I can divide by the total that we calculated before, the 3.6699 atmospheres. And guess what we get? We get out 0.6 repeating again, right? We get out the same value. Now you could do this exact same thing, right, for chi of Ne, right? And I recommend that you do it. Figure out the partial pressure of Ne, divide by the same total, and guess what you're going to get? 0.3 repeating, right? So the reason I'm showing you this in two different ways is, like I said, depending on the information that you're given in the problem, you might be given mole information. Well, then go ahead and just use that mole information directly and calculate mole fraction. But if you're given pressure information, notice, do you get the exact same value that we got with our mole definition if you just use our pressure definition? And the answer is yes. So either pathway works. You have to look at the problem and decide what information you're given to enact it. Okay. So that's it for gases. There are three different sort of equations we have to use. Sum the partial pressures to get a total pressure. Chi is either equal to N of a part over N total, or chi could be equal to pressure of a part over the total pressure. All right. And with those equations, right, you're able to sort of work your way through any mixture problem that you'll be exposed to. Right. So that's it for chapter 9. Good luck on the homework. As always, just to remind you, you might be sick of hearing it, but I'd like to say it, just to make sure you realize anything doesn't make sense, anything that you need in terms of help, make sure you reach out to me. All right. And like I said, good luck on these problems.